All right, we're taking a look at day 14 here, which is our congruent triangle proofs. We'll be doing day 13 tomorrow, so just a quick reminder. You should be finishing up day 14 for homework. We're going to go through what we went through into class today, and then we'll finish up with homework questions that you can take a look at in case you're having any trouble. So for this first question here, okay, we are going through the different congruency theorems that we can use. So just remember, when we have two sides and the included angle in between, this is angle, side, angle. When we have the three sides marked as side, side, side. We have the two angles and the side in between. This is angle, side, angle. We have the two angles, and instead of this, the side being in between them, it's one of the other two sides. This is angle, angle, side. And if we have a right triangle, we can use hypotenuse and leg. You also want to be careful with this because if you remember, we talked about doing the side-side angle theorem, which spells bad words backwards. We're not allowed to use that. We often call that the donkey theorem in class. All right. So just remember, we're not using the donkey theorem. Okay. We don't want to be bad words backwards here. So, all right. So we take a look at number 414, which is sufficient evidence. So make sure you're reading carefully here. Sometimes it'll say which is not. Here we're looking for is sufficient. And if you look at what we have, we go kind of question by question. We just have two sides here, and we know the three theorems we've been using don't have two sides only. They need two sides at an angle. Number one is going to be out. Also, remember that if you have the three angles, that's angle, angle, angle. This is for similarity, not congruent. That is also out. Number three, we have a sequence of rigid motions that moves these sides onto each other. So AB on the DE. So AB would be onto DE. Those would be equal. Okay, we have BC onto EF. So those are going to be equal. And then AC maps onto DF. So this is going to be true because of, we talk about here, side, side, side. And so this would be our choice that we would want to make. All right. If you look at number 4, the reason why we wouldn't choose this one is because it refers to points instead of angles. So we really would like this to say point instead of angle here. All right, going over to the right here with number 415. We have two distinct triangles. Now, there isn't a picture here, so I would really recommend when you're doing these questions to draw them out for yourself. So two distinct acute triangles, okay? So we're just drawing two acute triangles look the same. We have ABC and DEF. We're just going to label them in the same order. So there's ABC. We went around to the right. We're also going to label DEF in the same manner. And then we're going to go ahead and just mark off what we know. So we already know from the given, okay, that B is equal to E. So keep that in mind that that is a known thing. So the triangles are congruent when a sequence of rigid motion that maps. Now, if we map the angles onto each other, remember that's going to give us angle, angle, and that is not going to work. Okay, so that's out. If we map AC onto DF and then BC onto EF, those map onto each other, they're going to be congruent, but this, once again, leaves us with side-side angle. We talked about in the donkey theorem. We're not allowed to use that. So this is not going to work, okay? So careful with that one, all right? The other one we have is we map angle C onto angle F. So we'll put two arcs there. And then BC onto EF. And this would be enough because of angle, side, angle. And so that is the pick that we are going to make here. Once again, this mentions points instead of angles. So keep that in mind that would be the reason why we're not choosing number 415. Okay, 419. On the set of axes below, triangle A prime, B prime, C prime is the image after a sequence of transformations. It doesn't say what they are, but you can look at it and kind of get the idea of what they would be. Use the property of rigid motion to explain your answer. Are they congruent? So first of all, if you look at these, you can see that they are the same size and shape. And if we did a reflection, right, to get these mapped onto each other, we would just be reflecting over the y-axis here and then translating 3 units down. So we could go into detail about that, and that is something you can do. We can say that the triangle A prime, B prime, C prime is the image Still recording. All right. The image, I don't know what happened there. After a reflection and translation, you could say that these both preserve distance and angle measure. So they both preserve angle measure and side length, and then you'll be able to just basically say that they're congruent because of ASA or SASS, any one of those things. You also could just get specific to the fact that when you translate or when you perform the rigid motion, there was no dilation made. So the triangles are going to be congruent because the side lengths are the same. So as long as you mention anything about the fact that there's no dilation, or the triangles have the same side length, or that you've done a reflection and a translation, and these are rigid motions. But the big thing to mention here is that the side lengths and the angle measures are equal, okay? So if you want to get specific about what was done and then it preserves, then that would be enough, okay? For 416, we want to describe a precise sequence of rigid motions that's going to show that these two triangles are congruent. So number one, it doesn't say what triangle to move. So you can move either one. So if we want to take triangle ABC, okay, what we can do is think about, like, we want to get one of these two triangles to overlap something first. So if we were to slide, all right, this triangle to the right and translate it, we could get, okay, AC to map onto DF. And then all we have to do from here is reflect it over that line, right? And then when we reflect over the line, it'll match up perfectly. So those are the two moves we're going to make, okay? Now, it doesn't matter the order. So technically, what we could have done, right, is reflected the triangle over line AC. So we're going to get triangle ABC to move over here, and then translate it back. Just make sure when you do the translation, you're specifying what ray you're moving along, because there is no graph, so we can't just say right 6, okay? So we're going to say, first, because it says in order, we're going to say translate triangle ABC along ray, and just pick any two corresponding points. So we'll say that A is going to go on to D, because if you remember, this triangle is going to go over here first, and then we're going to flip it back this way. So we're going to slide from A to D, so along AD, and then we have to say when to stop, okay? Until A maps onto D. All right, and then we're just going to reflect triangle ABC over line DF. And we're done. That's all we have to do. Okay, once we reflect over DF, we're golden. The reason we're going over DF is because now our triangle's here, and this is the line we're going over. All right, 425 underneath this one. Which statement is not always true? This is important that it's not always true. Okay, now once again, they're giving us the label of the triangles, so we know that the order of the letters also tells us what angles are congruent and what sides when we pair up the first two letters, like A and D, right? B and E, and then C and F. Now, the other option you can do is just to draw yourself the three triangles and label them in the same order. So if we call it A, B, C in that order, we have to call this D, E, F in exactly that order. So if BC is congruent to DF, okay, BC and DF, look at that, they're not even in the right spots. And BC is the last two letters, and D and F are the first. So this is not always true.
If you didn't put them in the right way, then you wouldn't be teaching ABC.
Good call. So it could be equal if this was equilateral, but we don't know that, so that's why it's not always true. All right, if you keep going along the line here, A and D are indeed in the same position. You can see they're in the bottom left. They're also the first two letters, so they know that match up. The areas would also be equal because the triangles are equal, and so would the perimeters. So those two would always be true. So therefore, we can choose just choice 1. 427, right next door. Line EA is the perpendicular bisector of ZT. Remember, perpendicular means that we are getting 90 degrees, and bisector means that we're cutting something through and getting two equal parts. So we are getting 90 degrees at A, and we're getting ZA congruent to ZT. Which conclusion cannot be proven? Now, keep in mind, we can go above and beyond just saying perpendicular bisector because we have two triangles being formed, right? And we know that this side is always going to be equal because it's reflexive. And now we know that the triangles are also congruent because of SAS. So that means all the parts are going to be equal. So these two sides will be equal, ZE and TE. The angles up top here, ZEA and TEA, as well as angle Z and angle T itself. So, does EA bisect angle ZET? Absolutely, because we know those two angles are equal, so we can cross it off because it can be proven. Is triangle ZET equilateral? That we can't say. We can say that these two legs are equal, but we can't say is that they're equal to the bottom side. We don't know that. So we can't say that. We would want to choose choice 2 as our answer. But let's not stop there. Is EA the median? Absolutely, because it cuts the opposite side in half. So this is a median in the middle. And is angle Z congruent to angle T? We said yes, it is because of CP, CTC. All right, on to the next page here. Number 426. I says the two triangles below are congruent. Margaret says the two triangles are similar. Are they both correct? Now, these two sides are both 5 here. This side being 12 and this side being 13. So the first thing you want to do is note, like, how could we show that these two triangles are equal? Well, it's an option that we could use HL and try to show that these two sides are equal and then the hypotenuses, or we could try to show that these two sides are congruent. And if you think about it, we could just use Pythagorean theorem here. 13 squared minus 5 squared would be equal to b squared. Okay, that we'll call that b for this leg. And then we get 169 minus 25, which does turn into 144. And the square root of 144 is 12. And so once we know that this side is 12, we now know that those two triangles are congruent because of side, angle, side. All right, and then we can keep going. If they're congruent, are they similar? Remember that side, angle, side is not only a congruence theorem, it's also a similarity theorem. So we can say yes, they're both correct. The triangles are congruent and similar by side, angle, side. Also remember that if triangles are congruent, they're also similar as well. Not all similar triangles are going to be congruent. 431 in the diagram below. Okay, we have all the stuff going on here. We also know that AN is congruent to SC. And we want to know which additional statements are going to be congruent to show it that's congruent by angle, angle, side. So if AN is congruent to SC, what else can we get congruent here, right? Now, if we know that AN and AS and NC bisect each other, that is going to get these two lines to be equal, which the triangles will be congruent here, okay? But they won't be congruent because of AAS. They'll be congruent because of SSS. So this one is out, okay? We can go ahead and mark, or just erase these, maybe. We'll try working on that while we're going here. There we go. Okay, so this one's out because of side, side, side. Now, if K is just the midpoint of NC, okay, we also would know that the vertical angles are also congruent. So if these two are equal, K is the midpoint of NC, okay, this gives us angle side, side, which once again, can't be spelling bad letters in math class. So that's also not going to work. Okay, so this would be out because of the donkey theorem. And then if these two lines are perpendicular, well, that would just give us the same exact angles, congruent but 90 degrees. So that doesn't make sense either. So this would be the choice we'd want to make, choice number 4. And the reason being here is that if those lines are indeed parallel, then we would have the alternate interior angles here, congruent, both of them if we needed them, but that gives us angle, angle, side. So that would be our choice. All right, number 433 right below that one, given that the two triangles are shown, the other information that we have here that got kind of cut out here is that DB is congruent to BE. So we would also know that. So we're going to mark that on our diagrams here. That's something we know. And we want to know which statement could we use to show that these two triangles ABE, all right, and DBC are going to be congruent because of, and this is important, side, angle, side. So make sure you remember we have overlapping triangles or a bunch of triangles going on at once. Make sure you trace them so we know what is what, okay? And then we can start labeling pieces. So if we know, and we're going to go ahead and redraw this triangle off to the side here, okay? All we know right now is that this is equal. And this point, we have like a point D here. We'll do this in a different color. All right. We kind of have like this segment right here. We know this length. So keep that in mind. So what else do we know is equal just by looking at the triangles? Now, it's not the vertical angles because they're actually not parts of the triangles. It's this shared angle right down here. So right now we have an angle and a side. So either we need another angle, which would be angle E and angle D, right? Angle E here, we'd need this. That's not an option. We have E and D. Ooh, that would work, except that wouldn't be side, angle, side. That would be angle, side, angle, right? So that doesn't work. Angle F and angle F. Oh, that's the vertical angles. Remember, those are not in the triangle, so those wouldn't work. What about AD and CE? And this is kind of interesting. If AD was equal to CE, that actually would be enough. Because remember, we already know that this piece is equal. And if we add this piece on, we end up getting the whole segment equal and this whole segment equal. Well, the whole segment, right, would give us side, angle, side. What we need to do is we need to add AD plus DB equal to BE plus EC, and that would give us AB congruent or equal to BC. That would be these two sides. And that gives us side, angle, side. So this would be an option, would be congruent, correct? The last one, AE, over here, AE and EC, having this side equal instead gives us angle, side, side, and that's another donkey theorem. All right, let's go down the line here. We also don't need to do 528 because we did it above, even though the number's different. But 434, two right triangles must be congruent if. So if we have two right triangles, okay, why would they need to be congruent? If the acute angles are equal, that won't be enough because that'd be angle, angle. That would be similar. The lengths of the hypotenuses are just one side. That also doesn't work. The corresponding legs, important that they said both legs. That would be enough because of side, angle, side. And if the areas are equal, it doesn't necessarily mean they're equal because, for instance, if I had sides of, let's say, 4 and 3 here, right, which is 12, I could also do 2 and 6 and get the same area, right? This would be 1/2 of 12, which is 6. This would be 1/2 of 12, which is 6. So the areas would also not be enough. All right, over on the right here, only missing statements. So important part here is we know that the triangles ABE, so ABE is congruent to CBE. All right, so we know that these two triangles right down here are equal. All right. We also know that, oh, timeout. That's not angle. People, what are we doing here? Angle ABE, there we go, is congruent to angle CBE. So those two angles at the top are equal. Okay, angle ADE is congruent to angle CED here. Okay, and we want to prove that BDE is the perpendicular bisector. This line is the perpendicular bisector of AC. So the theory here is that if we can show, essentially, that these two triangles are congruent, right? two things. If we can get these two triangles congruent, all right, we can get these two sides equal, and therefore these angles equal, okay? A little bit of work here. Oh, no. All right. And if they're equal, then we can know that this triangle is going to be isosceles. Both triangles, the really big triangle and the small triangle, are going to be isosceles. And then this angle bisector has to be a perpendicular bisector because essentially it's an isosceles triangle. Okay, there's a few other ways you could have done this. You could have shown that these two angles are also equal. And if they're equal and they form 180, they have to be right angles. But that's not the way that this proof specifically is doing this. So let's go through and fill in the proof. So number one, we have the givens. Number two, anytime we see the same line is congruent to itself, that is going to be reflexive. All right. Number three, we have the angles are supplementary because linear pair of angles are supplementary. Number two, if these angles are supplementary, okay, meaning like BDA and ADE. The ADE is the angle that's right down here. These angles are supplementary to each other. Would it make sense that these two angles have to be congruent? And the answer is yes. And the way that we used to do this before is we would say that angle ADB plus angle ADE is equal to angle BDC plus angle EDC. And then all we have to do is subtract away angle ADB and angle BDC by subtraction. We're left with these two angles equal. And so one other way that they can do it that the Regents uses is that since these two angles are both supplementary to congruent angles, these two angles have to be equal. So what angles are they? Well, what angles are left over when we're done subtracting? That's angle ADE, that's in red here, and is congruent to angle CDE. Okay, that's enough to get these two triangles equal because of angle, side, angle. And therefore, these two sides, AD and DC, have to be equal, and AB and BC have to be equal because of CP, CT, C. So if those triangles are equal and those sides are equal, why is BDE the perpendicular bisector of line AC? And what we can essentially say is that the angle bisector of the vertex angle in an isosceles triangle is the perpendicular bisector of the base. And that would be enough. You have enough to get that point across because we have the fact that these two sides are congruent. The other option would be, once again, is just to explain that if these two sides are equal, okay, then the triangles are equal, and then these angles form 90 degrees, and since they add 180 and they're 90, they also have to be equal, okay? All right, let's go on to the next one. So what I'd like you to do, pause it for me. All right, so number 437, we have a parallelogram shown below. We have diagonals that are AC and BD that bisect at point E, essentially, okay, intersect at E. And we want to prove that these two angles, ACD and CAB, are congruent. So if you go ahead and you can label where those two angles are, you'll notice that they fall right there. And we know two key vocab words are the parallelogram and the fact that we have diagonals intersecting at E. We don't even need this, but it is an interesting point that we can bring up a little bit later. So number one, we have to show that those two angles are congruent. And the easiest way to do it is the fact that this thing is a parallelogram. And that means that we are going to have two pairs of sides that are parallel. And because they are parallel, they are going to make a Z, which gets us the alternate interior angles congruent. So the first thing we're going to say is the fact that those two lines, DC and AB, are parallel. The reason being, in a parallelogram, opposite angles are equal. All right, and once those two angles are equal, that lets us say that those two angles, where the base angles are congruent, so ACD and CAB, because two parallel lines cut by a transversal, the alternate interior angles are congruent. All right. Moving on. Number 435. So once again, we're putting our statements and reasons. We're filling in the givens with the word given there for the first reason. And key thing is we're going to look for some vocab words. So we see that we have lines that are bisecting each other. So that means they are both cutting each other in half. If each other wasn't there, we would think that RS is just bisects TV, but they're both bisecting each other. Remember, cut in half means that TV is cut in half. So TX is going to equal XV. And then we have the same thing here with RX and XS. Now, keep in mind that if we get stuck, that's what we can say. So let's go ahead and say that. So we can say that TX is congruent to XV, and in the same reason that RX is congruent to XS. Okay, remember the reason being that the bisectors, okay, cut the segments into equal parts. Is fine. And then you can just replace, if it's angle bisector, you can replace that word bisectors there, or segments with angles there. Let's fix that B. All right, next, if you get stuck, you might say to yourself, all right, man, I don't know what to do. Well, in order for these two lines to be parallel, right, or if they were parallel, then we would be looking for our favorite letter here again. Remember, we're looking for the Z. So if we can get these two angles equal, that will force these two lines to be parallel, because now these are the alternate interior angles, right? So if we get one of those angle pairs corresponding, alternate interior, alternate exterior, to happen, it forces lines to be parallel. There's also another pair of angles up here. We just need one of them, though. Okay, now, in order for that to be true, we're going to have to get these two triangles to become congruent, okay? That's what we're going to need. So we already know, rewind, okay? Maybe we're rewinding. All right, that these two sets of sides are equal. So another easy way to get the triangles congruent is just to get our vertical angles equal, and that's going to be choice 3. So angle TXR is going to be equal to angle, and if we say TXR, we'll go in the same order, so VXS, and that's going to be vertical angles are congruent. All right, and once those two triangles are equal, remember that means that we want to try to get one of these two sets of alternate interior angles. We talked about getting R and S, so we'll go ahead and say that. So angle R is congruent to angle S. Now we can't use the two parallel lines part because we're trying to show the lines are parallel. So we have to use the fact that we have congruent triangles and use CP. Oh, wait, time out. We didn't do the congruent triangles. We can't use CPCTC until we have congruent triangles. What are you doing, people? That means we're going to need to say that triangle TXR is congruent to triangle VXS because of SAS. And now we can use CPCTC because remember, it's corresponding parts in congruent triangles. So we got to get congruent triangles first, okay? And that will let us say that angle R is congruent to angle S. And we can use the two letters or just the letter R and S because it's the only angle there at that point. We can't use X because there's more than one angle. So we have to use the 3 letters in that case. And now we have enough to say that TR is parallel to SV. And the reason is because we have 2 parallel lines cut by a transversal. Okay. Alternate interior angles are congruent. And sometimes you might even just say 2 parallel lines cut by a transversal, okay, or 2 parallel lines cut by a transversal when the alternate interior angles are congruent. If you want to throw that in there, that might make a little more sense when we're showing the lines are parallel. All right. Let's go on to the next one. We'll pause it here. You can take a look at the answer if you'd like and check yours, and we'll go through it in a second. Okay, So number 442, we have a parallelogram. We have bisecting with DE bisecting NWD and REA at points W and E respectively. We want to prove that the two triangles are congruent. We got to do this first, and then we're going to carry on then to show that this is a parallelogram. AWDE, that this side in here is a parallelogram. So key thing, we have to get these two triangles to be congruent. All right. And then use those two congruent triangles to get this fact that this inside shape is a parallelogram. All right. So remember, we already know that the really big shape all the way around the outside is a parallelogram. That's given. So that means we can say stuff about the big shape that lets us get the triangles equal. So think about it. What sides in the really big triangle all the way around the outside, okay, are also sides or angles in the triangle? And the first you might see is this side RD and this side AN. So we can go ahead and say that RD is going to be congruent to AN. And while we're at it, we might as well throw in the other two sides. So we'll say that AR is also going to be congruent to DN, okay? And the reason being that in a parallelogram, the opposite sides, right, the opposite sides are congruent. Now, this is a little different than what the answers were a second ago, but that was one of the answers a little further down. Now, the other thing we're going to need, okay, is the fact that we have bisecting lines. So think about it. If this line ED is bisecting, that means it's cutting these two sides in half, all right? And more importantly, we already knew that these two lines were equal, right? These two lines were already equal with each other, okay? So if they're equal, when I cut them in half, I'm going to get 4 equal parts. So by rearranging step 2 and saying this first, what that lets me then say is that AE is congruent to ER, and it's also congruent, we can keep going here, with WN, and that's also congruent, all of those are congruent with WD. We can make one long statement about the fact that these lines are all equal, all right? And the fact is because we bisected congruent segments, okay? So when you bisect two congruent segments, you create 4 equal parts. Okay, so step 4 then, if now, let's think about it. In our triangles, because remember our goal is to get the triangles congruent, we have this side congruent, right? We have this side congruent. We need one other thing. And remember, the other thing that's going on in the triangle and the parallelogram is that they share these angles in the corners. And in the parallelogram, the opposite angles are congruent. So we can say that angle R is congruent to angle N. We don't need the other two angles where A and D are, so we can leave those out. And we can say that in a parallelogram, opposite angles are congruent. All right, and now do we have enough to get the triangles congruent? And yes, we do. So we can say that triangle ANW is congruent to triangle DRE. Remember what we have? We have side, angle, side. And then, why is it that this figure has to be a parallelogram? Well, remember, we already know that these two sides are equal, right? And now, since the triangles are congruent, we can get these two sides equal. And that's enough because we have opposite sides congruent. So 2 more steps here. 6, we want to say that AW is congruent to ED with, once again, because we got the triangles congruent, that's CPCTC. And for number 7, we're going to go ahead and make a statement that says that AWDE is a parallelogram. And then why is it a parallelogram? Because the opposite sides are congruent in a parallelogram, and that would be enough. All right. Let's finish up this last one here, and then we'll save these other ones for class tomorrow. So 441 in the diagram of a parallelogram, ABCD below. BE is perpendicular to CED. DF is perpendicular to BFC. Okay, so we have BE. Ooh, key thing, perpendicular. Love it. And we also have a parallelogram. Now, we want to prove that ABCD is a rhombus. So this is important. We already know that it's a parallelogram. We already know that this shape is a parallelogram. So keep in mind what we know about parallelograms. We know the opposite sides are equal, and we also know that the opposite sides are congruent. So in order for this to be a rhombus, okay, we just need to show that two sides that are next to each other are equal, because that forces these two sides to be equal, and now they're all equal. So all we need to do is get these two sides. Now the reason we're going to say these two sides, this side DC and this side BC, is because they're parts of these two triangles. And so this question is actually a disguised congruent triangles question, because if I can get these two triangles congruent, I can get these two sides equal, and I can make this a rhombus. All right, so let's see how we can do this. So what parts of these two triangles can we say are congruent because it's a parallelogram? Not a lot, right? Not a lot. Oh, we missed one thing. We also know that we have parallel lines, perpendicular lines. So that's going to get us these angles 90 degrees. Now remember, we only need the angles that are in the triangles, right? So really we just need this angle here on the right side of F and the angle on the top side of E. We really need those two angles to be equal, or 90 degrees and then equal. All right, let's go ahead and let's set up our proof. So you do your T-chart here, and we'll get. All right, we got all that stuff down. So now we have to add in what we just said about our lines being congruent. And I'm going to get rid of these markings here for the sides congruent because we don't actually know that yet, right? That was me explaining to you kind of the idea of what we need to do here. Okay, So we're going to go ahead and talk about those 90-degree angles. So we're going to say that angle, let's get specific, DFC is equal to angle, that's right, BEC. And those two angles are equal because they also equal 90. So we're going to say equal to 90. And then we're going to throw down a reason that the upside down T perpendicular lines make, this is important, we can't just say 90 degrees because we're comboing two statements here, make equal 90-degree angles. Otherwise, we would need to say that the two angles, okay, let's say angle 1 equals 90 and angle 2 equals 90, right? That would be one step. And the second step then would be to set angle 1 equal to angle 2 because of the transitive property. So we're kind of combining those two to make this one step here. And if you're watching this video and you don't have me as a teacher, follow what your teacher normally says. This is what we've gone over in class, so we're going to use it. Okay, second one. We also know that CE and FC are equal, or CF. So remember, if you're having trouble seeing what's going on, always redraw one of the triangles, okay? This will help you clarify what's going on. We have these 90-degree angles in the corner. We now have this side equal, so we need one more thing. One more thing. Let's think. Oh, can you see it? Right in the corner, these two triangles are overlapping, and when they're overlapping, they're sharing something. They're sharing this angle where C is. So this is going to be our reflexive property. So we can say that angle C is congruent to angle C. And the reason we can say that there's only one angle at C, this is the reflexive property, because we wrote the same thing is equal to itself. And can you see it now? We have angle, side, angle. So we have enough to get the triangles congruent. So triangle B, we'll say EC is congruent to, now keep that order the same. We went B to the right angle to our Reflexive angles, we're going to have to go DF to C. So triangle DFC. Make sure those are corresponding points there. And the reason, once again, is ASA. All right. And now that those triangles are congruent, how do we get this a rhombus again? We just need to get these sides equal first. Once these two sides are equal, then we can say that they're all going to be equal, okay? So 5, okay, we're going to say that BC is congruent to DC because of CP, CTC. And we actually have enough right now to say it, okay? We have enough now to say it. So depending on what you wanted to do, you could go a couple extra steps, okay? We'll do the shorter version, and then I'll let you guys, we'll show you what else you could do to get more specific if that doesn't make sense. You may not have done that on your own. So what we can say now is that ABCD is a rhombus, and the reason being that a parallelogram with adjacent sides congruent is a rhombus. Now, your other option, we'll call this 6A, was to do the opposite sides congruent and then use substitution to get them all congruent and say it's a rhombus. So we would say that BC is congruent to AC and BA is congruent to CD. And now that we know that these two are equal, BC and CD, right? We can say that BC is congruent to AC, is congruent to BA, is congruent to CD. That's going to be transitive. So opposite sides congruent. That's transitive. And then we can say rhombus because all sides are congruent. So whichever way you wanted to do, this is a couple extra steps, but that is also an option. All right. Try these two on your own, and then we'll go through these tomorrow as well. But for homework, you only needed to do pages 19 and 20. We'll see you tomorrow. Have a great day.